So it's 15:25, and this is the time for my talk, um, which is called implementing an MQTT client in Elixir. Um, I'm Martin, and me and my accent is from Copenhagen, Denmark. And this talk is about implementing a MQTT client in Elixir, and I want to briefly get into how to establish a TCP connection and some common things that goes into a binary protocol, and hopefully convince you to do a MQTT client of your own. So first, some expectation management. I only have 40 minutes or so to give this presentation, so I can't touch on everything, and I will grossly jump over some perhaps important stuff. But the thing is, I want you to try this out on your own, I think. I don't show much code. I don't find it particularly valuable to have lots of code on slides, because when I review code myself, I need 20 minutes to look at 5 lines of code and scratch my beard before I can make a decision. So yeah, try to stay away from that. And this might be high level at times and low level at other times. I've included what I think is important. So you will definitely need to read up on some stuff, and I will merely point you in the right direction. So let's start out with when we try to implement something, we want to know what it is. So MQTT is a client-server protocol, and it works by clients subscribing to the server, a centralized server, and clients can publish, and well, this effectively implements a pops-up pattern. So it's an open protocol. The spec is around 60 pages, and it is designed to be a lightweight messaging protocol for use in situations where network bandwidth and devices are small, and network bandwidth is at a premium. So as small bytes on the wire as possible, and the specification is designed to be able to implement the client part in fairly little code. So, the subscribing is working by our client subscribing to a topic such as room, living room, temperature, and the server will then deliver messages published to this topic to the subscribing clients. So the server is the middleman, and there's no way to send messages directly to clients. Clients can subscribe to as many topics as they want. So subscribe patterns. Say we have a bunch of devices in our house. The / is a separator, so you can make topic levels, kind of like folders in a file system. So say we want to, we have blob patterns. It's kind of like pattern matching. So the + is a single level wildcard, and we can put it wherever we want in our topic level. So this will subscribe to all the temperature sensors in our house. So there's a multi-level wildcard, which will subscribe to all topics under the room, which is every device in the house. One thing about the multi-level wildcard, it can only be the last, it can only be on the last position in the subscribe pattern. So when we publish, we can only publish to specific topics, so we cannot use blob patterns or wildcards. And a wildcard While a client can send a message to any topic depending on the server configuration. And there's no need to declare a topic upfront like you would in EMQP. They will be created as we go, as somebody subscribe or publish to it. The protocol doesn't define any format for the payload that we send, so it can be anything from a binary blob to a JSON document. So the protocol also specifies quality of service on publish and subscribe messages. The first level is level 0. It's a fire and forget. It just delivers the message to the server, and the server dispatches the message to all the subscribers. This is often used in cases where we have a temperature thermometer that spams messages to the server. In cases where it's not necessarily like 100% necessary to receive all the messages. There's a quality of service that guarantees at least once delivery. The message is sent to the server, and it will dispatch to all the subscribers. The server will then send an acknowledge message back to the client. One important thing I forgot to mention is we need to assign ID to the message before we send it, so that it can send a message back. And at that point, we can discard the message on the client. It will retry until it receives the acknowledged message. So, for quality of service 2, it guarantees exactly once delivery. It works kind of like the one we saw before. We assign an ID to the message. We send it to the server, which will send and acknowledge that it has received the message. At that point, the client will send back a message that it has received the message, so that it will not continue sending the same message. And at that point, the server will send it to the subscribing client and send a message back that it has done so, and the client can discard the message. So, why not use quality of service 2 then if it's so great? Well, it all depends on how much data we want to send on the network. We want to always send the smallest quality of service as possible. So the protocol has 14 messages, and 6 of them are commands that initialize something, like connecting to the service, publish, subscribe, unsubscribe, can send a ping or disconnect from the server. So 8 of them are forms of responses to this. So there are many neat features of MQTT, like retained messages, which will remember the last message that was posted to a topic, and so when you subscribe to that topic, you will get that message. Otherwise, it's basically you had to be there when the message was delivered. And there's last will messages that will, when you connect, you can assign a message that will be sent to a specific topic. So where you can use that for other clients to listen on a last will topic. So those clients can know when this device goes down or leaves the network. And there are secure connections, but this is an IoT talk, so I don't care about security. So why build an MQTT client in Elixir? my colleague Jesper has said that to fully understand a programming language, you must implement something non-trivial in it. And I find MQTT to be a good exercise because it involves some tricks and stuff that's really need to know as an Erlang programmer. And it turns out that MQTT and that Elixir is really good at doing this. It just have the right tools built in. And also for MQTT, we can control the environment because we can install and run our own server. Like VernMQ, it's a great server. It's open source. It's run in Erlang, so it's good. And there you can disable the security to allow anonymous logins, which make it easier to make the connect message. And we can install the client on a machine as well, so we can test the MQTT spec or server, how it all works before we try to play around with it ourselves. And we can start out by just implementing the simplest quality of service and then build from there. So it's easy to have success. So we need to be able to read the specs and make sense of them. And we need to open a socket and communicate with TCP. And we need to be able to encode and decode binary packages and be able to tell incoming packages from each other. And further, we need to keep state for some internal bookkeeping. I won't get into this in this talk. But let's start out by connecting to the TCP server. It turns out that the Erlang distribution already have everything we need for this. So, and it's hidden in the GenTCP module. And the function we are interested here is the connect message. So we specify that we want to connect to our local host and on port 1883, which is the standard MQTT port. And furthermore, we specify that we want to communicate with binary. This will send back an OK socket if we manage to create the connection. So the socket is a port, and I want to touch a bit on what that means. A port is a connection to the stuff outside of the beam. Ports can receive data. All communication with ports happens through message passing. And we can send data to ports that we know the port address of. So sending a message to a closed port will result in an error. And a port belongs to an owner process to whom it will hand over incoming messages and errors. Ports kind of sounds like a process. It's like the same semantics that we use to communicate with them, like message passing. But the huge difference is that we will get an error if we send something to something that doesn't exist anymore or has been closed. So first off, we create a process that can store our TCP port. And this is, through the slides, I will use this notation for processes. The connect message is the hardest one in the protocol. So for this presentation, I will just jump over it and not spend too much time on it. Hopefully by the end of the talk, we should be able to implement it. Because, yeah, and we want to supervise it, so we create an application with the supervision spec in it and supervise our receiver. So, receiving data from the MQTT server. We will receive a stream of octets from the server, and we need to know what it means to be a packet. Like, when does it start and when does it end? Because it will just be a stream of data. So, the specification has a figure like this. Says there's the package has a fixed header and a variable header and a payload. Some of them do. And the fixed header holds metadata about the package. The variable header has some structured data that is specific to that message type. And the possible payload is it's in messages where you can define a payload. So at this point in time, the fixed header is the most interesting because we need to figure out how long the message is. So this is the fixed header. If we look in the specification, we'll see this. It up here we have bits. I've seen it referred to as a bit ruler, so I like that name. Yeah, the seventh bit is the most significant bit, and the 0 is the least significant bit. It's the notation for binary. So if we read if we read this diagram out loud, it might go like this. So the 4 most significant bits of the first byte is the MQTT control packet type. The 4 least significant bits of the byte is the flags specific to the control packet. And the remaining, the 2 to whatever bytes encode the remaining length of the package. So we have something like this. This happens to be the notation for binary pattern matching. And it's a declarative syntax. We declare what kind of data we want to get out of the match, unlike regular pattern match where we just get the thing stored into a variable. So we can match on literals like any other pattern match, and for rest, like when you match on lists, you have to specify binary. From this, we know the type of package. We have assigned that to control packet. It's a 4-bit bit value, and the flags are kind of arguments. They are not used in every package out there. Notice that there's only 4 bits for the control packet. That means there's only 16 possible message type in the protocol. That means the protocol is pretty stable because I showed 14 before, so it's not like there will be much changes to that in the future. So more information, bless you. More information about the binary pattern matching is available in the Elixir manual. It's a pretty good manual page. So length prefixes. How do we read the length? How do we make sense of the package length? So if we have a string of 5 character hello, we can communicate it by saying there's 5 bits of 5 bytes in this message by just announcing 5 hello. This way we can scan for a number and then scan for a message of that number in size. So it comes in like pearls on a string, and so you can say we sacrifice 1 byte for length information, and this works great. But there's a problem. Like, what if we have a really long text? Then we can't communicate that with 1 byte. It's because we can only represent 255 in 1 byte. So we need something to deal with, like longer messages. Like we could use 4 bytes to denote the message length, but and this works for many protocols, like BitTorrent does this. But this presents us with a problem, because here I've made this diagram that the blue dots represent length headers and the gray dots represents data. So this is, like, say this is one byte for a length prefix. This doesn't make room for long messages. So if we convert to 4 bytes for a length prefix, then we will end up consuming most of the bandwidth for length prefixes, which is not good in a protocol where we mostly send very short messages. So MQTT solves this by having something called a variable length encoding scheme, which works like this. It's still a length prefix, and it uses between 1 to 4 bytes to represent the byte size. The upper bound is a huge number, and that's around 270 megabytes. It does so by sacrificing the most significant bit to communicate a continuation bit. So let's see how that works. Say we want to represent the number 60,210. It would fit into 3 bytes like this. So if I just show it in binary for now. The first byte is the continuation bit. 1 means that there will be more length information in this message, and 0 means that this is the end of the message. So effectively, we have 3 7-bit strings to communicate the length. Because of the way that the encoding works, we have to reorder the bit strings. So I've labeled them for clarity. Magic. ANC swept places. And if we put that together, we get a binary number that says 60,210. Make sense? Cool. And by the way, by prefixing a number in IEX with the 0B, we can write a binary number there in IEX like that, and in Elixir in general. If we want to write hex numbers, we can say 0x and then our number. So in a pattern match, it could be implemented like this. So we have the first byte that has a continuation bit, and we pull out the A, and then the second that has a continuation bit, and then the third that says stop, and then we reorder it like this, and then we pattern match it into a 21-bit number, and then we get our length. And notice that we need to have the same amount of bits on the left-hand side and the right-hand side. So this is a complete implementation of how we would do variable length encoding and decoding in Elixir for 1 to 4 bytes. If we get something that doesn't fit that scheme, we will just crash, because then the server has sent a longer message, and we don't want that. In general, when you implement these kind of protocols, if one of the parts does something that's not in the spec, you will just sever the connection, because rules are there to be followed. So this might look a bit scary, but look at the reference implementation. I don't know about you, I'm on vacation, I don't want to look at code like that. I would argue that the Elixir solution is much more readable. So just for, this is how we encode. We basically reduce the number until we has less than what we define as the high bit. We add the continuation bits as for long as we have that, and then and this also shows why we need to reorder before, because it's kind of reversed. So I hope this kind of diagram makes some sense now. So let's focus on the receiver. I tend to go for a state machine when I implement kind of stuff like this. And it just so happened that we have an excellent state machine in Erlang called the GenState, and ElixirConf has wrapped it in a nice library called GenState Machine that is available in Hex. So a GenState machine is a good way of modeling states and transitions between them. It's a process behavior, and as I said, it's included in OTP as GenState. The interface is kind of like a gen server, and it returns a tuple that decides what's next action to take. If it should transition into a next state, or if it should keep the state, or if it should stop, or whatever. So, like a gen server, it has a cast to and a call free for passing data from the outside into the state machine. And it's great when we have states that must happen in a specific order. So, we start in the disconnected state where we initialize and try to connect to the broker. And when we get connected, we will transition from disconnected to scan for fixed header. We receive data until we match on something that that matches the function that we just created. And when we got a fixed header, we will start receiving data for whatever amount of data was specified in the in the variable length information. And when we get a package, we will dispatch it to a function that will handle that package. And then we will return to scanning for fixed header. If we are kicked off the server for any reason, then we will just go back to disconnect, and then we will try to reconnect. So that is the state machine diagram for this sort of situation. So in the golden case, we will just continue receiving packages. Yeah, and from there it's just pattern matching. So sending data to the MQTT server. Our receiver deals with incoming data. So, whoa, I should be careful with my presenting notes. Sorry about that. So let us add a new process to handle outgoing data. Our receiver will be yet another state machine because I'm so crazy about them. And we boot into an awaiting connection because when I talked about ports, I mentioned that you can send data to a port. You just need to have a reference to it. So, but we, of course, don't have one when we start out. So we need to get it from the outside. And that happens by when the receiver connects to the broker and receive a socket, then we will, by side effect, send it to the transmitter, which will store the socket. So there are cases where when we lose the connection, the receiver will know about it because it will receive a message about it in its mailbox, and it will go back to just reconnecting and then send a new socket to the transmitter. So we need to be able to deal with a new socket coming in at any time. And in that case, we will just start using that instead. So when we post data, it can either go OK, or it can be closed because we sent to something that has been closed. So just to deal with that situation, we will be able to go back to awaiting connection, where if we try to send data at that point, we will use a feature in GenState that's called postpone, that will keep the messages around until the next state transition, at which point it will retry. So, yeah, we are now able to post messages in any state and send them when the transmitter is available. So it is useful. This is useful if we initialize our client and we try to send a message before we have connected to the broker. So we define a transmit function that will just take data and then do whatever it needs to encode it to the correct format and then pass it on to the TCP socket. Yeah, so now we have the logic in place for sending and receiving data. And yeah, it's basically just a matter of pattern matching at this point, and go through all the possible messages in the specification, and then there's also some bookkeeping. But I think the introduction to mix an OTP from on the Elixir website is an excellent guide to that, because it is basically a database at that point. So why build a MQTT client? To learn about TCP and how to use it, and familiarize, I should pick words that I can actually pronounce. Get used to reading protocol specifications and matching on binaries. Learn a bit about binary protocols and start experimenting with GenState machines. So as a encore, I'll just go through how to encode this to Elixir code. So the control packet is the number 12 in a 4-bit, which this is the syntax to use for that. There are no flags here, so that's just a 4-bit 0 and then a 0. So this is basically what we're dealing with when we send messages. That's about it. Any questions?
Coming.
Oh no.
So for the receiver, does it know because it was a ping? There's no length.
Come again?
For the receiver of the ping request, does it know there's no length? Therefore, there's nothing, no payload to decode.
You would encode it. You would encode the length in the message, cool, on the package, and I showed the code for encoding around back in the day. I hope what I said makes you capable of reading the specification. So, yeah. So, yeah.
Any other question?
Just wondering how devices discover each other on the network with MQTT.
Could you say that again?
How are devices discovered with MQTT?
How it was discovered?
Devices.
How the devices connect to the server. So the server has to be known. So it's just IP address on a network.
Anybody else? No more questions then? Okay. Thank you.